All right, so what did you guys notice about looking vertically at your slopes? What happens?
They're the same.
They're the same. Why do you think that is if this is your differential equation? You're only putting in x. So all of the points that have the same x value have the same slope. Okay? Okay. All right, so I saw some of the curves you guys sketched and they looked great. So I'm just going to start right here. And I'm just going to follow the slope pattern. This isn't great, but that's one of them. Now, this could be like this same shape, but maybe shifted to a different place. So how many of these curves could we have drawn? Infinitely many. There's no way we can draw them all, because we could shift up or down as many as we want to. Okay, let's find this general rule for y. So we have dy dx. If we want to find y, what we can do is find the antiderivative of our differential equation. So what is the antiderivative of 2x dx? X squared plus c. So do you guys think that that matches what we drew? Yeah, it looks like a parabola, right? And then the c is how many you shifted. So my c for what I drew would be 1.
Or it could be like 2.
Yeah, there's lots of different values for c. All right? Okay, so what we're going to focus on today is doing the slope fields, not necessarily doing this general rule. Trust me, we'll get there, but we're going to focus on slope fields today. All right, so flip over to the back. We're going to fill in a bunch of blanks. Now, a lot of times with things that you learn, you can kind of do it, like do the process, but not really know what it means. So I don't want slope fields to be one of those situations, because what you just did wasn't hard. You just plugged in x values and just drew little slopes. But I want you to understand why and what that means. So slope fields are a graphical representation of a differential equation that allows us to visualize the family of solution curves. So a slope field can give you a function family. What was the function family of the slope field we just did? Quadratics, right? So that's what we can get from a slope field, is to kind of know what, if we have dy dx, what kind of function that y is. So that is an important thing slope fields show us. All right, and then we just did this. So when we're making a slope field, we're going to calculate the slope at various ordered pairs. Then we're going to plot them, plot the slopes using short line segments, so little bitty line segments. All right, and then a solution curve will follow the trend of the slopes. And a lot of times you're given an initial condition, so a point that you want to be on your solution curve, and then you just draw the trend of the slopes through that point. And then if dy dx is undefined, do not draw a slope there. So it's just going to have some empty spaces where you don't have slopes drawn. It's fine. Okay, so on our first check for understanding, the first slope field we're going to do is for dy over dx equals negative y. So this time we only have a y. So before, when we went down vertically, those slopes were all congruent. This time when we go across, they should all be congruent. All right, so I'm going to start at the far left corner, top left corner. What is the ordered pair right there? -3, 2. So So the only one that matters for our differential equation is the y. So what is the slope going to be at that point? Negative 3, 2. Negative 2. So just draw the little mark that looks like about a slope of negative 2. Now as we go across, like if I go to negative 2, 2, the slope should be the same because we're just putting in the y. So as we go to the right, all of those slopes where y is 2 should be negative 2. Now, as you guys do this, if you want to do a table like the last problem had, you can do a table, but I feel like most of these you can kind of do in your head. All right, I'm going to go to the next row. I'm going to start at the left, so the point would be negative 3, 1. I'm going to put the y into my differential equation, so the slope is negative 1. So negative 1, or 1, is kind of like a 45-degree angle, if that helps you visualize it. But I don't want you to overthink it. All right, if I go down to the next set of points, I would have negative 3, 0. What are those slopes going to be? All 0, yeah. All right, and then the next row of dots, to the far left, we have negative 3, negative 1, so my slope's going to be 1 for all of those, because all of those y's have 1, or negative 1 as y coordinate. And then our very last row, we're going to have slopes of 2. That's it. That's the slope field.
How would you connect these?
We're going to do that in part 2. You want to go ahead and do it since you asked? Okay. So number 2 says to sketch the particular solution for dy over dx is negative y, which we just did the slope field for, that passes through the point 0, negative 1. So what we would do is go to that point 0, negative 1, and just go ahead and make a mark there. And then we're going to follow the slope trend, all right? So here, it looks like we have about a slope of 1. And then as we go down, it gets steeper. And as we go up, it's getting closer and closer to 0. So that's a pretty decent graph. Sometimes I do these better than others. Huh? It's not going to cross over because once it goes flat, it's not going to be unflat. No, okay. All right, let's look at the second one. This one is going to be more challenging. Why do you guys think? We have to use x and y. So we aren't going to have where the whole row or the whole column have the same slope. We're going to have to look at every individual points, but we can do it. All right, so I'm just, for some reason, I like to start at the top left. I don't know why, but that point is still negative 3, 2. Sorry, 3, negative 2. I was right the first time. I'm having an off day today. It happens sometimes. Okay, so we're going to put the x and put it over the y. So negative 3 over 2. So slope of negative 3/2 should be slightly steeper than negative 1. And definitely in the negative direction. So I would say about like that. All right, so would you guys want to go down from here or do you want to go over? I don't care. It's up to you. Okay, so then we're going to have negative 2, 2. We go over. All right, when I divide those, what do I get? Negative 1. right, and then negative 1/2. Zero. You guys got it from here? So just get each one of those points, just divide the x by the y, and graph a slope. What about this row where the x is 0, or where the y is 0?
There's nothing
It's
there.
undefined, so there's nothing there. Good job.
Yes or not? Have you ever seen like those airflow graphs or water flow graphs?
No.
This is exactly what it looks like.
Oh, cool.
You guys are smart.
Is it an engineering thing?
Yes.
Where did you see these airflow graphs? Is it a secret? That's pretty cool. All right, any questions on drawing the slope field?
Oh, I got you.
Okay, do you guys want to try and draw a curve through this one?
No.
You don't want to?
Wait, is there no starting point for this one?
I mean, we can make one up.
Oh, okay. 0, 0.
We can't do 0, 0 because it's undefined there.
Okay.
Let's do 0, 1. All right, so as we go out, it gets flatter. Kind of weird. Kind of like that. And we can't cross where it's undefined. All right, any questions? And one thing they love to put on the AP exam are questions where you have a graph of a slope field and you have to match it with the equation that would be a general solution or a solution to the differential equation, which we haven't found yet, but we will. So we're really looking at these slopes and determining what function family this would belong to. So y equals e to the x. What does that graph look like? Like, draw it with your finger. Well, it's flat, a horizontal asymptote, and it curves up.
It's not that one.
It's not that one. We all know y equals is a parabola. Is it that one? No. What about the natural log of x? Yes, it's flat and it curves up like that. It has a vertical asymptote. And then sine is going to do something like that. That's not real great, but something like that. So we're definitely talking about the natural log function family here. That's not too hard. The other thing they'll do is give you a slope field and ask you to match it with a differential equation. So it's the one that all these slopes match the equation. So that's, to me, a little more challenging, but we'll practice that tomorrow. Okay, and then last one. This is a good review of using tangent approximation. So anyway, we're going to let y equal f of x to be a particular solution to this differential equation satisfying f of 3 equals 4. We're going to write the equation of a line tangent to f of x at x equals 3. So let's just do that first. What two things do you need to write a tangent line? The slope of the tangent line and the point of tangency. Do we have one of those already?
Yes.
What do we have?
The point.
And it's 3, 4, right? All right, do we have what we need to find the slope? The differential equation gives you the slope. So I would take this differential equation, and we haven't done this notation a lot. When we plug something in, we're going to do a straight bar, and what we're plugging in is the point 3, 4. So we'll put 3 in for the x, 4 in for the y. Our line is going to have a slope of 3/4. All right, and then we'll just write our equation using the point slope formula. Now, I'm not going to multiply it out just because it's going to make it easier for us if we don't. Now, we might want to do this. Just move that 4 over. Okay. All right, so the last part is we're going to use this line to approximate the value of f of 3.1. So I'm going to take my tangent line approximation, and I'm just going to plug in 3.1 for x. All right, now let's do this without a calculator. So let's think about in terms of decimals. So we all know 3/4 is 0.75. What do we get when we subtract those? 0.1. So what do we get when we multiply 0.75 by 0.1? 0.075. Good. And it's super easy to add 4 to that. Oops, hold on. There it is. That's a good review of some stuff we haven't done in a while, tangent line approximation.